I am excited to share a paper entitled Imitating Past Successes Can Be Very Suboptimal. This is a story about a really simple reinforcement learning method, one that you might have used before. We show that it can fail, and then we fix it. So what is the simple method? It's often referred to as goal-conditioned behavioral cloning. Here's how it works. Let's say you have this robot, and you want it to push the red block to the green goal. But this is what the robot actually does. It fails to reach the commanded goal, but it succeeds in reaching some other goal. And so this is a good demonstration of reaching this other goal. So we can apply behavioral cloning to this experience, conditioning on the goal that was actually reached. The same idea has been applied in a variety of contexts. For example, if we use language, we can learn a language condition policy. If states are labeled with scalar rewards, we can learn a reward condition policy. And even methods that filter or do reweighted behavioral cloning can be viewed as special cases. I'll refer to all of these methods as outcome-conditioned behavioral cloning. And I'm interested in two main questions. Do these methods maximize some notion of rewards? If so, what reward function? And second, do these methods always produce a good policy? The main contribution of this paper is drawing a connection between these conditional behavioral cloning methods and reward maximization. And to do that, we need to precisely describe how the experience gets first labeled and then relabeled. Let's say we have some state S and action A, and the environment gives us some label for the state. That's what I'm calling E. This could be a language description, it could be some text, it could be some rewards. For concreteness, let's say that it's the XY coordinate of the block. And then we're going to go to the next state and get its location of the block, and so on. Now, what we really care about is what happens after we visit a certain state in action. So after the first state in action, there are many possible labels that happen, each corresponding to a different XY location of the block. And so we might say that this first state in action were good for achieving these different block locations. Now, we're going to sample one of these future labels and call it ET+. And we'll place a higher probability on sampling one of the outcomes in the near-term future. Precisely, I'll use this geometric distribution, where the term in blue says, look at the label that occurred T steps in the future. We then go and relabel all of the future states as well. Now, how does this relate to maximizing rewards? Well, this distribution over future outcomes, it looked a lot like the expected reward objective, where this term looks like a reward function, and this term looks like a Q function. And by applying Bayes' rule, we can directly see what conditional behavioral cloning should learn. It should look like this policy shown on the right, that's composed of two terms. The first one corresponds to averaging together policies, and the second one corresponds to improvement. Let me show you what that means. In the simple example, we have two tasks and we have two policies, and each policy is a distribution over actions. The averaging step corresponds to computing a mixture of these two policies. And the improvement step corresponds to reweighting this mixture by the task reward. For example, the rewards for task 1 are higher for small actions, and so we increase the likelihood of those small actions. Now, for this example, we see that the rewards after conditional behavioral cloning are actually lower than those of the initial policy. Behavioral cloning is worse than doing nothing. There's a nice geometric interpretation of what's going on. Let's think about a different setting where we have 3 tasks and 3 actions, so each policy can be plotted as a point here, where the x-axis is probability of sampling action 1 and y-axis is probability of sampling action 2. The stars denote the optimal policies for the 3 tasks. I'll randomly initialize the policies. The averaging step will bring these policies all together, and the improvement step will pull them away from each other, drawing each closer towards its optimal policy. Now, what happens when we iterate this procedure? We learn the optimal policy for the blue task, but very bad policies for the orange and the green tasks. And these tasks are easier than the blue task. This example shows 2 things. One, it shows that conditional behavioral cloning can actually make a policy worse rather than better. And second, iterating can make the policy worse and worse. And this is potentially surprising because prior work suggested that iterating sometimes makes things better. Now, the underlying issue here is the averaging step. And in our work, we remove this averaging step using a simple form of normalization. This allows us to learn the optimal policy in this case. On 4 benchmark tasks from prior work, we get roughly the same performance, perhaps because the data distributions here are relatively close to uniform. But on versions of these tasks with bias goal distributions, we observe much bigger boosts in performance. So we've drawn a connection between behavioral cloning and reward maximization. There are a lot of interesting future directions I didn't get a chance to talk about. Please stop by the poster to learn more. Thanks.